Thank you very much. My name is Claudia Cardoso. Yeah, this is kind of a joint presentation because Dario is the developer of one of the methods that I will talk about. And I will continue in the same idea of the previous presentation, of Alberto's presentation, to talk about more or less practical and technical aspects of the YAML code and of the GW calculation. So So again, in a very brief way, here are the Hedin's equations that Alberto showed before, and also other speakers, in the form of this pentagon. And if we are able, and we know that we can calculate the energy of excitations as a correction to, let's say, a mean field calculation, for instance, a Kohn-Sham calculation through the calculation of this self-energy here. So to compute this self-energy, we can use the Hedin's equations in a self-consistent way. And at some point, we arrive at a green function whose poles correspond to these excitation energies. In practice, we usually don't do this self-consistent cycle, or very often we don't do this self-consistent cycle. We do a G0 W0 calculation. This means that we start from a mean field calculation, like a DFT calculation. We compute the G0 green function, and then we use this green function to compute at the independent particle level the polarizability, the reducible polarizability, then the screened interaction, and finally the self-energy. So we ignore this part of the pentagon that are the vertex corrections. So again, here there is the self-energy that is given as a product of a green function and the screen interaction. This is a non-local operator that depends on two sets of variables in two moments. So we have the creation and annihilation of a particle that occur at two different moments in space and time. So if we focus only on the time dependence, we can write the dependence of the self-energy as it's dependent only on the difference between these two instants in equilibrium, as we have seen before. But the GW calculation is done in frequency space. So how do we obtain, how do we go from the dependence in time to the dependence in frequency? We do a Fourier transform. So when we do the Fourier transform of the self-energy, instead of this product of the green function and the screen interaction, we have now a convolution. We have this integral on the frequency. Okay, so let's say the building blocks of the green functions are the correlation between the creation and annihilation of particles into different moments in time and space, as I said before. So, for instance, if we take the retarded green function written in an Hamiltonian formalism, to do the Fourier transform, we can consider the Fourier transform of this heavy side. There is this heavy side part of the green function here that has this form, and we arrive at the retarded green function that has the dependence on frequency on the denominator, and then the eigenvalues of our system also in the denominator. We can do the same for the time-ordered green function. Now we have two terms. with the states above and below the Fermi energy. And we can see that the time-ordered Green function now has poles. If you imagine this is a frequency plane, the poles of this function are just slightly above or slightly below the real axis of this frequency plane. If we, for instance, apply this Green function, use a Conchamp basis set to explicit our Green function, we have this expression here, where again we have the frequency dependence on the denominator. We have this energy, so if we take a Conchamp basis set, the energies correspond to the Conchamp energies. So we have here the Conchamp energies, and then the projectors on our basis and the occupation of our states. So this is, let's say, the explicit dependence of the Green function, the explicit dependence on frequency of our Green function. Okay, so we have part of the job done. This is our self-energy. That, if you remember, it's a convolution between the Green function and the screened interaction, screened Coulomb interaction. We introduced the expression we obtained in the previous slide here, and now we just have to deal with the representation in frequency of the screened interaction. That is actually the hardest part. So this can be done in different ways. So the frequency integration of the self-energy can be done either, let's say, I separated here in a very crude way the methods in numerical integrations or full frequency integrations or analytical models. And then there are many others. The ones I will focus on are the ones implemented in YAML. So in YAML we have this, so the numerical integration, what I mean by this is that W is computed numerically, explicitly in many points in frequency. And this can be done, if you recall, the self-energy integration is done along the real axis. So this can be done by computing W in many points in a frequency grid along the real axis, or it can be done in different ways that I will explain briefly in a moment. Instead of computing repeatedly W at several frequencies, we can approximate W by an analytical model and introduce an analytical expression in the integration of the self-energy, and this facilitates the integration, and it's much more efficient computationally, so your calculation will be much faster. There are, I think, the most common approximation is the Plasmon-Pole approximation that is implemented in several ways with several variants. The one implemented in YAML is the Godbinitz implementation. And I will also talk about another analytical model that has been very recently implemented in YAML, that is the multipole approximation. So this will be the focus of the rest of the talk. Okay, so as I said before, this is our expression for the self-energy dependence on the frequency. We have introduced the frequency dependence of the Green function, and now we need to look at the frequency dependence of W. So these two quantities, we want to do the integration along this axis here. This is the plane, the complex plane of frequency, and we see that these two functions have poles that are very close to the real axis, which make the integrand he'll behave in this region. So if we want, if we want to do numerically an integration along that real axis, we have to be very careful. But that's precisely what is implemented in YAML. So in YAML, let's say the full frequency real axis implementation considers, so takes this expression, then uses the symmetry ordering of the symmetry of W, that is symmetric with respect to the, let's say, the imaginary axis here, or to 0 in the real axis, transforms the integral that goes from -infinity to infinity in an integral that goes from 0 to plus infinity, and has now this expression here. So what we do, as I said, we compute W in a grid along the real axis frequency. So for points omega 1, omega 2, omega I. And in between, we assume that W varies linearly. So for an arbitrary omega, W is given by the linear variation between its extremes. So for points in between the grids, we assume a linear dependence on the frequency, and the corresponding parameters are computed at the grid points. Okay, we introduced this expression in the self-energy, and in the end we have the frequency dependence for the self-energy. So as I said before, this has to have a good representation of the frequency variation of the self-energy, we have to compute W in many points of the real axis, and it can be numerically difficult because you can have instabilities here, and in the end you have to repeat the W calculation. That means computing the polarizability using the Ising equation and arriving finally to W. So it's a very time-consuming calculation, and you have to do it for hundreds or thousands of points along this line. So it can be very time-consuming. There are other ways that I put again in the numerical methods category, that instead let's try to replace the integration along the real axis by an integration along the imaginary axis. So somehow there is like an analytic continuation of these quantities into the complex plane. So instead of having a real frequency, we have now a complex frequency, and we try to find a path that allows us, for instance, in this case, to exclude all the poles of W. So we have inside this path only the poles of G, and we can say that, so usually these integrals along this part go to 0, and we can say that the integral along this closed path is equal to the sum of the residues inside. So computing the integral along the imaginary axis and knowing the residues of the green function, we can determine the integral along the real axis. So this is one of the methods. There are others, and there are variations of these methods. That they are not implemented in YAML, but they can somehow improve the efficiency of the computation, because since you don't have poles along this imaginary axis, the integrand is much better behaved, so you need less points in your frequency grid to compute the self-energy. So going now to the second category of implementation, the analytical models. The most common and most efficient one is based on the Plasmon pole model. In the Plasmon pole model, this takes into account that for many materials, the dielectric function is described by only one pole, at a frequency that is called the Plasmon frequency. So we can approximate we can model the macroscopic dielectric function by a function with only one pole. This pole corresponds to a collective charge neutral excitation that we call a plasmon, and has a characteristic frequency, a plasma frequency. So we can use this model, where this model has two parameters, this omega and this omega tilde, and the square of these parameters are related to the plasma frequency that can be determined, for example, experimentally or theoretically with ab initio calculations. So the Multipole approximation corresponds to use that description, but not for the macroscopic dielectric function, but for each of the matrix elements of the dielectric function. So each elements of the dielectric function, and then, of course, the polarizability, are described by a pole and a residue. This is the model. This is the model in frequency. So this Z is the frequency, an imaginary frequency here. This is our model to describe the frequency dependence of the polarizability that then will determine W, that will enter in the self-energy. So we have, again, two parameters, and there are many ways of determining these parameters. The most known ones, the most common, are the Iverson and Louis methods, where these parameters are determined by recurring to a Kramers-Kronig equations and to some rules. And then there is the Godbinitz method, that is the one implemented in Yambo, where these two parameters are computed by computing the polarizability numerically for two values of the frequency, and then these two values of the polarizability are the ones that allow to determine the parameters of the rest of the frequencies. This is a very simple model and a very successful one. And between all the variations of the Plasmon pole implementations, in fact, the Godbinitz one is the one that has better agreements with respect to full frequency calculation. So here the comparison, you can see a study of the several implementations of the Multipole approximation in this paper. And here we think that the benchmark would be like the benchmark of the numerical calculation instead of the experimental value, because of course there are other factors that influence the comparison. But if we compare these implementations to, let's say, benchmark full frequency calculations, the Godbinitz implementation is the one that gives better results. Okay. It's a very good approximation. Of course, it's very, very efficient. You just have to compute W for two frequencies instead of hundreds or thousands. So it's much more efficient computationally than the numerical approaches. Of course, it has limitations. The accuracy of the quasi-particle corrections decreases when you go away from the Fermi energy. If you have a screened interaction that has a very complex structure in frequency, here you see graphene. The Plasmon pole gives you just one pole, no, just one peak to describe a very complex structure in frequency, and this can affect your results. So in some cases, in many cases, it's not enough. It's hard to predict the accuracy of the implementation, so because it's system dependent, and conceptually you can think, how can we use an approximation that is thought for a system that has a collective excitation in, for instance, finite systems in molecules. So it has been used, and it's more accurate than expected, maybe, but conceptually there are some problems. The imaginary part of W is not described, so you don't have quasi-particle lifetimes. It doesn't describe satellite peaks, and these are the main. But it works in many cases, and it's very efficient. So we can go a step further, and this is an approximation, an implementation that is very recently in Yambo. Is just in the last release of Yambo, and from now on you can use it. That is the multipole approximation. It was introduced here in this paper. It was mainly developed by Dario, that is in the audience, so you can ask all the questions to him at any time. And the idea is to generalize the model where you take the polarizability that is described by one pole. Now you allow the polarizability to be described by a sum of poles, but a small number of poles. So otherwise we would fall in the case of the full frequency case, now that we can calculate this polarizability so many times. Now we want to limit ourselves to a small number of poles. And now we are considering a frequency that is imaginary instead of real. So what does this mean? We are trying to, instead of describing single particle transitions, again, we are describing collective transitions, but now we can have more than one branch. And this, if you use, if you have an expression of this kind, you directly arrive at analytical expression for the self-energy that you can very easily integrate. So how do we, so this is the expression, a sum of this type of terms with poles, the omega and the residues. That, as in the case of the Plasmon pole approximation, we have to determine. And this is not as easy as it can seem, and after many trials and errors, we have arrived to a sampling. So we have to determine our polarizability in a number of frequencies that is twice the number of poles, because we have to determine two parameters for each pole. And so we will calculate numerically the polarizability in the complex plane. Here are this is a toy representation. Here are the position of the poles. As you see, around the poles, the function varies very rapidly, and then it gets more uniform if you get out of far away from the poles. So we have found this sampling that corresponds to doing a sampling so along the real axis of the frequency, one that is more or less close to the region where we expect the poles to be, and another one that is further away. So this way we keep some of the structure of the poles, but in the end we have like a mixture. We have a smoothing, a broadening of this function that can be modeled with a small number of poles. Okay, so here are the calculations, so the benchmarking of this model. You can see this is the real part of the polarizability, here the imaginary part, and these are different matrix elements of the polarizability for HBN. So you can see, for instance, in this one that is very clear, that with one pole, so let's say our benchmark is this full frequency calculation in red. With one pole, this is not the Plasmon pole approximation, it's just the multipole approximation with one pole that should be more or less equivalent. We are not able to describe the polarizability in all the frequency range. But if we increase the number of poles, 1, 2, 3, 8, we increase the description, and with 8 poles, we are on top of the full frequency representation. So we are able to describe the polarizability with 8 poles. We have, so if we do convergence tests, we have the same number of poles for all the matrix elements. So they are described with the same number of poles. They are not many, they are in this case 8. And we are able to describe both the real and imaginary part of the polarizability. Okay, I've shown you the polarizability, but we want the self-energy. So we did our multipole approximation, we plug it in W, and now we compute the self-energy, and we want to see the results of how the self-energy is described and how the quasi-particle energies are described. So you see here the plots for the self-energy, and again, so here the plots include two different states, a valence state and the conduction state. Again, the red and orange are the full frequency benchmarks. And you see, so this is the Plasmon pole result here. And you see that the multipole is on top of the full frequency. And this is the self-energy. And you can see that in an improvement of the quasi-particle band gaps of these systems. Of course, these systems are very simple semiconductors. So the differences are not huge. But in more complex, in more complex systems, like here, for instance, for copper, that is a metal, you can see how different the self-energy and the spectral function. So here is the self-energy, the spectral function, how different the Plasmon pole and the full frequency and multipole approximations are, and so the solution of the quasi-particle corrections is given by this intersection here of this line with the self-energy. And you can see that for copper, the improvement also on the quasi-particle energies is considerable if you go from Plasmon pole to multipole or full frequency approach. So I think I'll end here. I will just mention that this multipole approach can be combined with other methods. For instance, the method just described before by Alberto Guandalini, and it has been implemented in Yambo, the combination of the multipole and the W average method. And just to illustrate very rapidly, you can see here, so the combination of these two methods is that you are accessing the computational cost when you are doing calculations both in frequency and momentum transfer. So you are speeding up simultaneously in these two parameters the calculations. You can see here the calculation of the Fermi velocity at Dirac point for graphene. And you see that when we use the combination of these methods with very small, well, not that small, but fairly small K-grids, we are already converged and we are within the experimental results, while if we don't use these methods, we would need to go to very, very large K-grids to reach convergence and reach the correct value. So I finish here. There are several methodologies addressing the frequency dependence of the GW in the GW calculations. In Yambo, you have the Plasmon pole, the full frequency in the real axis, and now the multipole. Your choice of these methodologies should be a balance between accuracy and computational cost. And you can think that the computational cost is proportional to the number of times you have to compute W in frequency. So for the Plasmon pole, you have to compute twice. For the multipole, you have to compute, let's say, up to 20 frequencies. And for the full frequency, you have to compute several hundreds or thousands of points. If you cannot use the Plasmon pole approximation, the multipole leads to a level of accuracy comparable with full frequency methods at a much lower cost. So it's now implemented in Yambo, and there's already a tutorial that you can follow if you want in the wiki of Yambo. And I finish here.
Okay, so we are running a bit late, but I think we have time for one quick question, if there is any. Okay.
Thanks, very interesting. Just a curiosity. So you mentioned that this is so the multiple implementation, or so the taking into account more poles in the description is would be important for say molecules or reduced nanosystems, basically, right? So
well, no, I mentioned that there are some conceptual problems in using the Plasmon pole approximation for finite systems, but it seems to work fairly well. So it's not. I think you need to use. You need to go beyond the Plasmon pole when you have either poles that are very close to zero frequency, so you have numerical problems in accessing there. So you compute the polarizability very close to zero. If you have a pole there, you'll have numerical problems. This can happen for metals, for instance, or for systems that have a very complex structure in frequency where the polarizability, or W, has a very complex structure in frequency, and you cannot describe them by one pole. Maybe hybrid systems where you have, let's say, a Plasmon pole that comes from two different parts of a system or something like that.
Thanks.
You want to?
Yes, just to add a small comment, another example is when you have a multiple solution for the quasi-particular equation. And with the Plasmon pole, you will get one probably. So you want to describe this, you need to go beyond Plasmon pole.
Okay, so I think we are late now, so we close the session now, and now it's time to go to lunch finally. Yeah, we can.